Okay, in this video, we're going to look at concavity and points of inflection. In this section, we're going to be examining how the second derivative can be used to establish concavity, concave up or concave down. And we're going to start by considering the first derivatives of the following functions. Okay, so let's take a look at when a function is concave up. For concave up, as x goes from negative infinity to positive infinity, so as x increases, the first derivative goes from a negative value, and the reason why it's negative is we can see that the slope of the function here is negative, and then it goes to 0, and the slope of the function then goes to a positive value right there. You don't have to draw those lines in your notes. I'm just drawing them to show you that we're going from a negative to 0 to positive. So as x increases, dy dx, so the first derivative, also increases, right? As x is increasing, the function is going, or the first derivative is going from a negative value to 0, and then the first derivative becomes positive, so the first derivative increases. If the first derivative is increasing, then the second derivative is positive. So a function will be concave up if the second derivative is positive. Now let's look at the next example for concave down. Okay, as x goes from negative infinity to positive infinity, the first derivative goes from, well, let's just take a look right here, positive to 0 to negative. So it goes from a positive value to 0 at the max, and then to a negative value. So as x increases, dy dx is decreasing. Right? We can see it's going from positive to 0 to negative. Okay, so therefore it's decreasing. If the first derivative is decreasing, then what that means is that the second derivative is less than 0, and so we say that a function is concave down for the values where the first derivative is, or rather the second derivative is less than 0, right there. The x value where a function switches from concave up to concave down is called a point of inflection. At a point of inflection, the second derivative is either 0 or undefined. Okay, so the point where it goes from concave up to concave down that's going to be a point of inflection. Okay, at every point of inflection, the second derivative is 0. However, not every point where this is true is a point of inflection. What must happen is you must have a sign change. Okay, a sign change must also happen across that point. Okay, so it has to go from concave up to concave down. So concave down to concave up to concave down, concave up to concave down. Right. That's what we call inflection points. So as we can see here, the second derivative is going to change signs. Okay, so here we go. Example 1. For find the points of inflection for this cubic. Use a sign table for the second derivative. Note that there are no discontinuities for this function. Okay, so we're going to go ahead and we're going to find the first derivative. So let's find the first derivative right here. So y prime is equal to 3x squared plus 6x minus 9. So then y double prime is just equal to 6x plus 6. And in its factored form, that's 6x plus 1. Okay, so we're going to set this equal to 0. All right, and so therefore x is equal to -1. So this one right here could be a POI. We're going to do a sign table to see if it switches from concave up to concave down or vice versa. So let's do a sign table. X is less than -1, x is greater than -1, and then we have the second derivative, 6x plus 1, second derivative right here. And we see that for values of x less than -1, the second derivative is negative, so overall we have a negative value. Okay, this means that for values less than -1, the function is concave down because the second derivative is negative. Look, we said that over here. If you want to come back and see it, it's concave down at all values of x where the second derivative is negative. Okay, so second derivative is negative, concave down. Over here, this would make this positive, and so therefore the second derivative is positive, and so therefore it is concave up. Okay, if it's concave up here, but it's concave down right here, and right at -1 it's equal to 0, that means we've got a sign change, and it's going from concave down to concave up, so that means that it's a point of inflection. So -1, and then right here I plug -1 back to my original function to get the y value. -1, 17 is a point of inflection. All right, moving on to the next example. Find the points of inflection for this quintic. Okay, so I'm looking at this quintic right here, and I'm going to find the first derivative. Okay, so let me just go ahead and find that first derivative. So y prime is equal to 15x to the power of 4 minus 40x cubed plus 4. Then I have to find my second derivative. My second derivative is going to be, well, I can like find it and factor it, right? Because I would get right there, I'd get 60x cubed, right? Minus 120x squared. And if I have 120x squared, so what I could do right here, and this is x cubed, I can factor it, and I would get 60x squared x minus 2. Okay, and then I'm going to find my values of x that make my second derivative equal to 0. Okay, so I'm going to set my second derivative equal to 0. So therefore, either x is equal to 0 or x is equal to -2. So I'm going to test these out using a sign table here. Okay, so using a sign table, I can go x is less than 0. Look at my first factor, 60x squared, x minus 2, and then overall, what's the effect on the second derivative? Then I go between 0 and 2, and then I look at x greater than 2. Okay, for 60x squared, this one is always going to be positive because the x value is squared. But when we have right here x less than 0, this is going to be negative, this is going to be negative, and that's going to be positive. So that means my second derivative is going to be negative, negative, and that is positive. Okay, so over here we see no sign change. We can see that the second derivative is concave down before 0, and it is still concave down after 0, but before 2. Over here it's concave down, but then over here it's concave up. So because there's the sign change right here, therefore I can say that this is the only sign change. All right. So that means 2, -57 is the only point of inflection. And it's basically going from concave down to concave up at x is equal to 2. Okay, let's look at this next one over here. Find the points of inflection for y is equal to x to the power of 1 over 3. So I'm going to find y prime. Y prime is 1 over 3, x to the -2 over 3. And then over here, this is y double prime, and I get -2 over 9, x to the -5 over 3. Okay. So what we have over here is we have, another way of writing this is -2 over 9. And then in the denominator, I would have x to the 5 over 3. Okay. So when x is equal to 0, okay, the second derivative does not exist. So I'm going to create a factor table for values of x below 0 and values of x greater than 0. Okay, so this is my second derivative right here. So values of x below 0 would make this positive. Values of x above 0 would make this negative. And so therefore, after 0, it's concave down, and then right at 0, it's concave up. So 0, 0 is a point of inflection. Okay, in the second derivative test, we can basically find the critical points where the first derivative is equal to 0. So where the first derivative is equal to 0, that means we have a min, we could have a max, or we could have a flat POI. All right, if the first derivative is equal to 0, then find the second derivative and sub that x value into the second derivative. So if the second derivative is positive, then the point is in a concave up region. And so if it's concave up, but the first derivative is 0, that makes this a minimum. If the second derivative is negative, then the point is in a concave down region, but the first derivative is 0, so that makes this a maximum. If the second derivative is equal to 0, then the second derivative test doesn't work. So we're going to find the critical points for this function right here and then classify them using the second derivative test. So what I'll do right here is I'll find y prime. I'll find the first derivative. Okay, note that there's no restrictions to this cubic function right here. And so y prime is equal to 12x squared minus 12x minus 24. Again, I'm going to factor this out. I think we've seen this one before. Maybe we have, maybe we haven't. Here we go. And I factor this. So I've got two critical numbers, x is equal to 2 and x is equal to -1 would cause the first derivative to equal to 0. So that means that 2 could be a max or a min or flatten POI, and -1 could be a max, a min, or flatten POI. So what I'm going to do is I'm going to now find the second derivative. And so the second derivative here is equal to 24x minus 12. So I'll start with x is equal to 2. I'm going to sub x is equal to 2 in there. Y double prime is equal to 24 times 2 minus 12. Well, 24 minus 2, 24 times 2 minus 12 is 36. And so therefore, y double prime is greater than 0, which makes it concave up. Okay, so when x is equal to 2, the region is concave up. But when x is equal to 2, the first derivative is 0. So that means that 2, -39 is a minimum. When x is equal to -1, I'm going to sub that in right there. Y double prime, 24, -1 minus 12. Okay, I get -36, so y double prime is less than 0, so that means that it's concave down. If it's concave down, that means that -1, 15 is a maximum, right? So at -1, the function is concave down, but -1 makes the first derivative equal to 0. So that means that it is a maximum. Now, if I look at this right here, this is a cubic function, and cubic functions can only have local maximum or minima because they go towards positive infinity and negative infinity. So this one right here is a local min, and this one right here is a local max. Okay, so that is using the second derivative test. So in this lesson, what we've basically done here is we found a way to find the POI. Remember, the POI is a value where the second derivative is equal to 0 and undefined, and you have a sign change across that value. That makes it a POI. Like we saw over here, this made the second derivative not exist, but we did have a sign change across it. So that means that it is a POI. Same thing over here. We had the second derivative equal to 0 at x is equal to -1. There was a sign change, so it was a point of inflection. All right. Okay, great. Thanks for watching. Homework is listed.